The first speaker will be Lawrie from Heidelberg University talking about F theory and ADS-CFT2. So please.
Thank you. Okay, this works. Seems like it works. Good. So first of all, I just want to say thank you to the organizers. It was a great pleasure to be invited here and to talk about some of this work we've been doing over the last year or so. In this situation, we is various different permutations of this set of authors. So initially, this program started by thinking about field theories that are somehow related to F-theory constructions. For example, field theories where you assume that the coupling varies over some part of spacetime. And this is sort of what we originally tried to do. Now, it turns out that these kind of field theories are very hard to study in general, because they have a varying coupling, they have some non-perturbative effects, and they're difficult to understand from a field theory point of view. So this led us, in this next paper here, to start thinking about what we called ADS solutions of F-theory. Define exactly what I mean by this in a moment, when my slides come back. Okay, I can keep talking. So the idea there was that you could learn something about these field theories by constructing some ADS duals. And we did this in general for some specific types of ADS and some specific amounts of supersymmetry. And one subset of our authors then produced paper 2.0, where they looked at some other examples with varying different amounts of supersymmetry. And then there is this upcoming paper, which should come out, I would say this week, but I feel that would be overly optimistic, so let's say next week. I realize I missed an X. Okay, so let me jump straight to the first definition that I have to tell you. So what exactly do I mean by an F-theory solution? Well, an F-theory solution just means that I want a type 2b solution, but I have some notion of the varying 10-dimensional axiodilaton over some part of spacetime. And more than this, we actually want it to incorporate somehow the full monodromy structure of the duality group of type 2b. And since we're thinking about the monodromy of the axiodilaton, then this is just sourced by Seven Brains, as we all know, and Seven Brains is inherently F-theory. So it is in this sense that I talk about solutions of F-theory. Now, we want to consider solutions with an ADS factor because we want to understand the dual field theories. And what we do is we take what's known as the top-down approach to ADS-CFT, whereby we take the 10-dimensional killing spinner equations and we solve them for some specified amount of supersymmetry. This is something which it turns out we can do, but incorporating the full SL2Z monodromy is a little bit tricky. So this had not been done before. What had been done was, of course, things like simple poles in the axiodilaton or these kind of variations, which were sort of done a few years ago in these papers. Now, we do this principally because we want to understand the dual CFTs. And as I said, these can be very difficult to understand because I have PQ7 brains somehow in the spectrum, and these give us some kind of defects, some kind of genuine non-perturbative effects. The field theory approach to these kind of dual CFTs can be difficult. And so why I titled the talk F-theory and ADS3 CFT is that I will mostly talk about ADS3. There are some other examples with ADS5 that I might get to, but mostly we'll talk about ADS3. ADS3 is, of course, dual to 2D SCFTs, and we have at least some understanding of where 2D SCFTs come up in F-theory. We know at least two places, so let me tell you one of them. One of them is that they occur in what I could call the string sector of F-theory. So in any F-theory compactification, I can take my elliptic fibration, that elliptic fibration has a base, and I can wrap a D3 brane around any curve inside of that base. This will give me some string-like excitation in the effective field theory. So regardless of what you do or what you want to do, these things will always be elements of the spectrum. Whether they're interesting elements or not somehow depends on what you're interested in, but they're certainly always there. And it turns out, of course, that the world volume theory of the string on the SCFT has different amounts of supersymmetry. Compactifying on a K3 gives you somehow maximal chiral supersymmetry. Calabi-Yau threefold gives you 0,4, which I'm sure many of you know from the superconformal field theory story. And then in 4 and 5 dimensions, you get a 0,2 CFT on the string. So as in the 60 case, these strings can tell you something about an interesting part of the moduli space. Again, if you're familiar with the SCFT story, then these things, when they become tensionless, they signify superconformal sectors of your F-theory compactification. So I just want to tell you now a little bit about these strings. So there are sort of two main kinds of strings in 60 compactifications of F-theory, what I can loosely call the rigid and the non-rigid case. So the rigid case is relevant for the SCFTs. And one reason why these strings are interesting, for example, one of the computations in this paper was that you can compute something like the instanton part of the Nekrasov partition function in an appropriately 6-dimensional definition by relating this to the elliptic genera of, let's say, states of k-bound strings. So in this sense, you can kind of bootstrap interesting information about the 60 theory by knowing something about the 2D SCFTs on these strings, which are just some 2D 0,4 theories. And some parts of these theories we will highlight in a few minutes from an ADS perspective. So another approach, or the non-rigid approach, is where you consider just a 60 supergravity with the curve inside of the base, which now has some deformation modes. And one can also wrap a D3 brane on this. And this is then related quite nicely in this paper to microstate counting about black holes in 5D. Okay, so that's 60. Let's just quickly think about 4D and 2D. So in 4D, n equals 1, these strings are dual to instantons, but in this case they're not BPS, their tension is not protected, and there is, maybe, it's not quite so clear, but you can see this paper for more details, there can be some quantum corrections to the tension. Okay, and then in 2D, once again, one finds actually that these strings are a necessary part of the spectrum. So this is now like F-theory compactification on a Calabi-Yau 5-fold, which were studied a couple of years ago in these two papers. And you find that there is a tadpole condition which requires that you wrap a certain number of D3 branes around a certain curve class. And in this short paper from, I guess, 2016, we put sort of these ingredients together from the Calabi-Yau 5-fold compactification with understanding the D3 branes giving rise to the strings to show somehow that F-theory compactifications to 2D were anomaly free. So these strings always arise. So now that hopefully I've motivated you as to why we might be interested in the kind of field theories that are going to be dual to the ADS solutions that we have, let me tell you what we're going to say for the remainder of the time. So in the first case, you can do something directly in a field theory case. That's if you take a single D3 brane and you wrap that D3 brane around a curve. Then we have field theory tools that allow us to do something there. Unfortunately, these tools do not generalize to the case of multiple D3 branes, and so we lack explicit construction. However, what one can do is one can construct supergravity duals with 0,4 supersymmetry. So this is now going to be like the string in 60. And one can determine some data like central charges or anomaly polynomials by studying the holograph. Okay, so this is sort of stuff from last summer. And then I want to tell you about a couple of new things. So when we solved in this paper the solution for ADS 3 and 0,2 supersymmetry, we only really had an understanding of the 0,4 duals. But in this paper, my graders pointed out some solutions, some special solutions with 0,2, and some interesting observations about 2,2 from the same construction. And finally, if we get there, I hope we do, because it's a nice little digression to finish with, I'll tell you something about an alternate way of computing this kind of information about central charges and anomaly polynomials of these theory from a much more field theoretic approach. Okay. So let's first of all start with the field theory, and I'll be very fast about the field theory. So if you have a billion n equals 4 super Yang mills, then Intriligator told us in the 90s that actually you have an additional U1 symmetry, which was called the bonus U1 symmetry. And it can be defined just as follows. Associated to each SL2Z transformation, you can construct a U1D transformation. And it turns out that if you just look at the objects in the vector multiplet of n equals 4 super Yang mills, they actually transform in a well-defined way under this duality symmetry. Of course, you might say it looks a bit weird. The self-dual and the anti-self-dual parts of the two-form transform differently and so on, but this is just somehow capturing the fact that it's to do with the variation of the coupling. And further, there is a connection associated to this U1D symmetry, which you see just looks like the variation of the coupling. And then there was this procedure which was laid out in a paper of Luca from a few years ago, where you could do a kind of topological twist. She called the topological duality twist, where one didn't only turn on some background gauge field along the curve to cancel the curvature of the curve, but you also turn on some background U1D field to cancel the variation of the supercharge across the curve of that U1D. So this is similar to your usual topological twisting procedure. And so we did this for Calabi-Yau 3, 4, and 5 folds. And for example, you can compute something very solid. You can compute the central charges. So these central charges actually already appeared in this paper, who did the 60 case of the topological duality twist as well. And so there are a few things in this talk that you should keep in mind throughout because they'll come up again and again. So one is essentially this C right here, 3C.C plus 3C1B.C. And similarly, one can determine the anomaly polynomial for the 0,4. That one will also come up again, but I won't ask you to remember it. Okay, and the anomaly polynomial that you derive via this kind of duality twisting procedure matches exactly the anomaly polynomial just worked out from a field theory approach to strings in 6 dimensions, which was done in the mid-2000s by Berman and Harvey, and then more recently by Shimizu Tachikawa. So, okay, great. Now, how do we generalize this to multiple D3 branes? Well, this U1D is actually violated by the interaction term in these fermionic variations. So there's no obvious extension of this topological duality twist to non-abelian n equals 4 super Yang mills. So one alternate approach that one can take is to instead consider M5 branes. And this is what Benjamin and Sakura did in this paper in 2016. So a D3 brane wrapping M4, now not thinking of a curve, but now thinking of it wrapping a full 4 manifold, is dual to an M5 brane which wraps an elliptic 3-fold, i.e. elliptic vibration over M4, with now just a purely geometric twist. And you know, the magic of the M5 brane takes into account the fact that the coupling varies in the 4D theory. Of course, you somehow push around your difficulty because now you have to think about the non-abelian case as working with multiple M5 branes, but it turns out one can make some progress by considering a single M5 and then doing this Cordova-Jaffer's procedure of non-abelianizing the resulting compactified action. And you get some non-abelian n equals 4 super Yang mills with varying tau. Now there's one big subtlety here, which is that so the 3-7 strings, or the 7 branes intersect this 4 manifold in some complicated way, and this gives rise to some complicated defects related to variations of the coupling. And actually understanding these defects is pretty tricky. So we looked for a different method, and we thought about ADS-CFT correspondence. So in the ADS-CFT, of course, I have a notion of large n, and if we can correlate this with some large number of D3 branes, then we would be in business. Okay. So now is the part where we actually come to talking about the ADS. So what does that mean? That means, as I said, I want to construct a solution of type 2b supergravity, where essentially this object P1 is non-zero. So one assumption that we actually make, one place where we're slightly not general, is that we choose to set this free-form flux to 0, and we just consider theories supported by 5-form flux. Okay, so there's a general starting ansatz for the metric, which just decomposes into some warp factor, some ADS, and some auxiliary 7 manifold. And then the F5 flux decomposes in the usual way, and if we want to preserve some 0,2 supersymmetry, we have to solve some Killing spinor equation. Luckily for you, I won't go into all the details, I'll just tell you the answer. And the answer is that the 7 manifold here is just a circle fibration over some 6 manifold. This makes sense. The circle fibration is just giving you the U1R, superconformal R symmetry of the 0,2 theory. This somewhat, well, the part that you may not have expected if you were not an F-theorist, is that in this solution, the tau variation actually combines into an auxiliary Kähler elliptic fibration over this M6. So this is now a 4-fold elliptic fibration, and it satisfies some non-trivial constraint. Key thing to note is that this constraint is equivalent to Ricci flatness, so one does not require, of course, this elliptic fibration to be Calabi-Yau. Of course, you look at this equation and it's a little bit tough. So you think of what you can do a little bit easier to start with, and first of all, we thought, well, let's look at some more supersymmetry. 0,4 supersymmetry is interesting. It's dual to strings in 6D. So let's do that first. We also can see some 2,2 supersymmetry later. Okay, so if you require, in fact, 0,4 supersymmetry instead of 0,2, it turns out that everything splits up very nicely. So this M6 splits up into a product of an S2 and some B2. And in fact, the elliptic fibration is purely over the B2 part, so you end up with a now really a Calabi-Yau 3-fold. And the circle fibration combines into the Hopf fibration over the S2, which gives you the SO4 isometry. Or gives you an SO4 isometry. So one thing to note is that the Killing spinners transform only under the SU2 right. That is, the SU2 right is the superconformal R symmetry. And there is always an additional flavor symmetry in these theories, which just comes from the rotations transverse to the string, if you think of that construction. In fact, I'm not telling you something. So actually, there's ever so slightly more general solution where you can quotient this out by some finite subgroup of SU2. And the same supersymmetry, of course. So in this talk, I will consider only ZM quotients. So actually, I wouldn't consider these too much, but occasionally you will see an M, and I just want you to know that this is this M. Okay. So let's just say, so the general F-theory solution, so general now, with 2D 0,4 supersymmetry in the dual, just looks like ADS3 times S3 mod gamma times an elliptic fibration over some B2. And it has some F5 flux corresponding to D3 branes, and it turns out that this curve, which is wrapped by the D3 branes, actually has to be ample in the base. So this is something of an important point because before I told you about 2 different kinds of strings in 6D, rigid and non-rigid, it turns out this necessarily corresponds to the non-rigid case as the curves are then ample. So one can ask something about why one does not see the rigid case. Okay. And just to point out, these solutions are just generalizations of the previously known solutions. ADS3 times S3 times T4 and ADS3 times S3 times K3. Of course, these are just the cases where the base is such that the elliptic fibration over it is trivial and you're at constant coupling. Okay, so what can we do now? Well, we can compute, for example, the central charges from a holographic point of view. As we know, the central charge is effectively just proportional to the radius of ADS. And as one plugs in and tidies up, replacing the volume by some intersection theoretic data, one can see that the leading order contribution to the central charge, just this 3n squared m c dot c. So if you remember earlier, I told you to remember 3c dot c. There's 3c dot c again. Okay, this is the leading order contribution. You can also compute subleading contribution. I won't really tell you this in any detail, but you can use the Chern-Simons couplings and you can gauge this S3 isometry to determine the contributions at subleading order in n. And so I just summarize central charges now to all orders in n as computed from the ADS CFT dual. Notice that if we set n is equal to 1, we recover what I told you to remember from the spectrum, as we would hope. So in this case, from the type 2b supergravity, we only really understand it from the point of view, the subleading corrections at least, where m is 1. The reason for this is that m somehow counts a number of KK monopoles in the system. And I don't really want to talk about this, but it sort of then becomes somewhat tricky to compute these for large numbers of KK monopoles. However, one can do this via an alternate procedure where you T-dualize a solution to an M-theory solution, and then the KK monopoles become M5 branes, and one can compute the central charge there. And we will do that. So let me just give you a brief recap. So we constructed general solutions of type 2b with 0,4 supersymmetry in the dual CFT. The things to note are that, of course, the coupling varies, the exodilaton, so that's exactly what we wanted. And we picked the case where we turn on no three-form flux. The geometry was of this form, and the flux was through an ample curve, i.e. corresponding to n d3 branes wrapping that particular ample curve. The dual CFT is exactly the world volume theory of a string in a 6D F-theory compactification. Did I start at half past? Okay, good. So I will skip the bit in the middle that I would skip. So this is this bit. So one can, of course, dualize to the M-theory solution, which was known before. One can see this. And is just related to the MSW string, wrapping some divisor inside of some linear system on the elliptic vibration. One can compute the central charges also from M-theory, and the point is that these match exactly with type 2b for the case of m equals 1, which we can compute in the type 2b. Okay. So I don't really need to tell you the summary again, since I went through that bit very fast, but you can compute, for example, central charges, and we did this in various different ways. We looked at the 11-dimensional supergravity dual, which I just did incredibly quickly. We looked at some construction of strings in 6D, and we did some anomaly inflow from an M5 brane point of view. And this all verifies the computations. And of course, it matches the direct spectrum computation, which of course is only available for n equals 1. Okay. So now I want to tell you about something a bit more recent from December of this year. So if you remember that the general solution to preserve 0,2, which I told you very quickly, was that it's ADS3 times an S1 fibration over Y4, where Y4 is an elliptic fibration that's not necessarily clear. This elliptic fibration must satisfy this rather complicated condition. And this condition is somewhat formidable to solve in general. So one thing one can do is look at some interesting special solutions. In particular, you can look at solutions where the base of the elliptic vibration factors. So I just want to stress this point, of course, that I4 now no longer needs to be Calabi-Yau, which is sort of in contrast to the case where you have a transverse flat space. Like Minkowski. Okay. So here are a couple of solutions. So these two solutions in this paper were called the universal twist solutions. So either you consider a product of a curve and a surface for the base, and you assume that the elliptic vibration either localizes over the 4-manifold or over the curve. So you end up with either an elliptic surface, that's this S2, as part of the Y4, or you end up with an elliptic threefold. That is, it's a product of a non-trivial curve with an elliptic threefold, or of a 4-manifold with an elliptic surface. Notice that none of these factors required to be Ricci flat to preserve supersymmetry. And actually, we understand now the dual CFTs to these universal twist solutions, and they can be seen as arising from taking 4D n equals 1 SCFTs and doing exactly a familiar topological duality twisted reduction on a curve that I told you we did for n equals 4 a year or so ago. So this procedure generalizes in this way. The other thing that they noticed in this paper is that if you ask for 2,2 supersymmetry, and you require that this object Y4 is a compact elliptic vibration, then actually Y4 is necessarily trivial. So there are no compact 2,2 solutions where the axiodilaton varies. It's sort of a noteworthy point. So one point which I will not write, but we'll just say, which is interesting here, is that they pointed out in this paper actually that if you show compactness, you find that this space actually turns into an appropriate foliation of the ADS3 by ADS5, and you get solutions that correspond to 4D n equals 1 SCFTs. I can't really say much about that. So at the moment, these guys plus maybe do one more, are studying these dual theories for the 4D n equals 1 SCFTs. So I can't really say anything about that at the moment. Okay. So now I'm going to change gears a little bit. So if you kind of dozed off a little bit, now would be sort of a good point to wake yourself up for a quick finale. So we actually would also like a field theoretic approach to computing some of these things. So one thing which is interesting and has come up recently, so this paper was from Friday, maybe Thursday, and this paper, well, it had a revision put out last week as well. So the idea is that you could take an anomaly polynomial for a certain SCFT, and you can add to that anomaly polynomial, or for a certain field theory, you can add forms which are proportional to things defined on the moduli space of the couplings. So let me take you through the example that these guys did, which is theories of class S. Theories of class S are kind of easy to discuss the anomaly polynomial because they come from an M5 brane wrapping some Riemann surface. In this case, I'll ignore the punctures. And so one can just integrate the M5 brane anomaly polynomial, which works very well, over that Riemann surface, some anomaly polynomial for the class S theory. And if you do this, as was pointed out in this paper of these guys, one finds that the anomaly polynomial integrates to something like this. Now, what is this thing? This thing is kind of the bit where all the details are contained. They tell us that this is actually the relative tangent bundle of C over the moduli space of curves. And the integral of this, by some classic mathematical result, is actually proportional to the Weyl-Peterson metric on that moduli space. So from this point of view, one can see that the class S theories, they have an anomaly polynomial which contains some classic stuff, and then it contains a term which looks like the Weyl-Peterson metric, or that appropriate cohomology class. So what we were thinking was whether one can do a similar story for the duality group of n equals 4 super Yang-Mills. And it turns out that you can. So I'm just writing it down here. So usually I would write down the anomaly polynomial of n equals 4 super Yang-Mills as just this expression. There is an SU4 cubed anomaly in the R symmetry, and that comes with an n squared. In fact, if you carefully derive it, in fact, we derived it in a couple of different ways by including this U1D symmetry, then you find that there are also terms of this form, where this C1LD is now somehow related to the U1D symmetry. We can do a topological twist of this along the curve and compactify to get the two-dimensional theory. So we determine the anomaly polynomial of the 2D theory just by integrating this anomaly polynomial, which looks like this. Notice that this is the same as the anomaly polynomial that I told you some time ago. And we can compute the central charge. The central charge just minus the coefficient of this term in the anomaly polynomial, and it looks like this. You notice 3n squared c dot c plus 3n c1b dot c is exactly the central charge that we also compute via holography. So it matches the supergravity dual. So in this way, we have sort of a field theoretic approach to understanding also some of these things, some aspects of these theories, like anomaly stuff. Okay. Okay, so let me conclude very quickly. So what we wanted to do was start exploring supergravity backgrounds with varying axodilaton, which we call as ADS solutions of F theory. And we constructed ADS3 solutions. They preserve 0, 2, 0, 4, 2, 2. For the general 0, 2, of course, we know how to solve this complicated equation, but we can solve it in special cases, and we can solve the 0, 4 always. And the 2, 2, it turns out, has no compact solutions. We really have a microscopic understanding for the 0, 4 theory, which is as the world volume theory of these strings in F theory. And there's sort of an obvious question. So one question is exactly, what happens when we turn on some three-form flux? Then that would allow us to determine somehow every ADS3 solution with 0, 4. But that's a bit more tricky. And then another question you might ask is, I only talked about the 0, 4 theories on the non-rigid 6D strings. What about the rigid ones? For example, the strings of the minimal SCFTs, whose central charges, etc., are written down in Delzodo-Lockhart. In this case, the curve wrapped by the D3 branes is not ample, so how does one gain some understanding of their ADS duals? Nothing more to add on that at this point. And just thinking about this notion of anomaly polynomials with terms related to the duality symmetry seems to be fairly powerful. We can find information about the field theories with varying coupling, some non-perturbative stuff, and we can sort of extract some interesting information. So extending this to think about 4D n equals 1 models with F-theory duals, what those additional coupling terms would be, is sort of one thing to do. So in this paper, I should say they did some, for example, YPQ 4D n equals 1 theories. They looked at adding these kind of anomaly polynomial terms. And in this paper, we look at n equals 4, which you should see next. Okay, thank you.
Thank you. Questions, anyone? Thomas?
I was wondering, you said that you're considering solutions of F-theory. How far do you really treat the 7 branes carefully in this theory? Because it seems more like you're doing type 2b and switching on some axiodilaton profile, which might
That's right. So how careful would you...
No. I mean, do you do something else with the 7 branes, or do you take them into account?
So,
I mean, they can carry fields, and we know that there's matter and everything.
That's right. Okay, good.
Like
so
most of the complication in the rest of the F-theory talk is precisely not what you're saying here.
Absolutely. So what we do is that we assume that the 7 branes intersect bit of space-time that we want tau to vary over in some transverse way. So they essentially just source some local monodromy. So if you do this story with the M5 brane, so at some point I talked about the M5 brane being dual to the D3 full 4-manifold. In this case, I said there was some duality defects. Essentially, the fact that the 7 brane data in that case is more complicated, because you can have a much more complicated intersection pattern between the 7 branes and the 4-manifold. Various different codimensions. For the case of curves that I talked about, essentially the 7 brane just intersects transversely. So in that sense, so there is a 3-7 string sector, which I didn't talk about, but the 3-7 string sector in this case of the curve is fairly straightforward.
Alessandro? So you showed us an equation for the Ricci scalar and Ricci tensor on the base, right?
This one, yes.
So I was wondering if that comes from a consistency condition, some SUT structure on the base that might actually be easier to solve. I mean, where does it come from?
So there is an SU3 structure on the base. So this comes. Oops.
So I can motivate my question a little better. So okay. For Calabi-R, one doesn't solve actually the condition R min equals 0 directly.
Right.
That's why the Calabi-R reformulation is useful. One writes the conditions on the SUT structure, but many are easily solved, and then one reduces the problem to a Monge-Ampère equation. I mean, there's a strategy there.
Okay, so I can tell you where this equation comes from in this sense. So there's this M6. The M6 is some SU3 structure, and then there's some stuff that includes this one form P, which is proportional to the variation of tau. So if you just construct the solution, you end up with some complicated equation, and that involves this P. And what you notice is that if you just take the structure of this P, where this P locally looks like d tau, then you find actually that the whole expression can be tidied up and packaged together like this. So
is this equivalent, an equivalent formulation, or a local equivalent, or?
So it's local in the sense that there are 2 sides of the things that you do away from the location of the 7 branes. So for example, this object P is being d tau. This is something which is true, of course, away from the 7 branes. So indeed, so basically you know what this kind of thing is for an elliptic vibration. as in how it decomposes along the fiber and along the base. And you notice that the solution you get is exactly of the same form. As in, that's what allows you to repackage it.
Thanks. Okay, anyone else? If not, then maybe thank Greg again. Thank you. And